Recording now. Just checking whether the recording really works. Yeah, it is started. So welcome everyone. We keep it the way that when you want to say something, you raise your hand or something like this, so that I can see it, so that we can manage this in an effective way. The first hour will be a climate control discussion. We have some open topics we want to address today. And the next part of the next hour will be about, let's say, machine learning, but in a bigger scope, all that is involved on the all-sky cam from the fisheye until something is recognized on the fisheye. So this whole realm. For the newcomers, I want to introduce you to Sky 360 in a way to say we are developing hardware and software. And we developed this in 6 teams. We have 6 teams. The first team is a master control program team, which controls everything, all devices, all sensors. The second is the all-sky cam. Christian, go ahead.
Show the diagram we have.
Yeah, I'd like to. I hope I can. Because I'm sitting only on one screen right now. I have to share. All right. Oh, this is complicated. Hold on. Share. Share. So, are you seeing what I'm seeing?
Yeah.
Okay. So this is the master control program. This is one team. One team is the all-sky cam team. Then the PTZ team, the climate control team, the GUI team, and the enclosure team. So depending on
maybe show the concept graphics about how things interact with each other. Yes,
right,
that one.
that one.
So we built up for each green box a team that covers several features of it, and so we do not put everything on just on one shoulder. That was the idea.
Yeah, okay. That's what you wanted to say. Got it. So
shall I explain it, or just can we keep on with can we keep on going with the 6 teams? I think this is much more important.
yeah.
Yes. Okay. Go on, Richard.
So we're now talking about climate control. This is one part which controls the climate inside the station. And we came to the point where we say we were very much confessed that we need a closed loop system, not an open loop system. Because when open loop, we always are getting the climate from the outside inside, and we have to compensate for it. If we can make a closed loop, then all the energy that is spent to create this climate is less, and we have less issues, and especially with harsh environments like salty fog environments and so forth, so that the electronics are kept in a good shape. Another more important point is that it should be a maintenance-free situation. So the whole station, as we envision it, is a maintenance-free situation. So when we set up this station on a, let's say, on 3,000 meter on a mountain, it is not the idea that someone goes there every week or every once a month. It should be running 24/7 unattended. So therefore, our goals on, let's say now with the climate control, are a little bit more complicated, let's say. I give you a short introduction to the climate control, what we think it is, so that you get an idea about it. We have an enclosure which is of the size 70 by 30 centimeters. It looks like a mortar throw upside down. Underneath, on the bottom side, are two openings. One is for the air intake and one is for air outlet. I have a prototype running for over a year, and it is in let's say an Austrian environment, and it's working in winter and in summer. But we have situations where there is more dust in the air or salt in the air, or it is even colder than in Austria or even hotter than in Austria. All kind of weather situations should be covered with this climate control device. So with this, the box that is underneath two holes, we want to attach a climate control device on both holes, so to ventilate the air between those holes.
Richard, would you mind switching over to my stream? I can show a picture of the box.
Yes, please do that.
You continue talking. I'll
Yeah,
illustrate.
please share it. Please share it.
Can you see it?
Coming.
Yep.
Now it's there.
Okay.
So what you see here is in transparent is let's say the enclosure, but Brad shows also parts on the ground floor where the two openings are, on the very right front and on the left back. No, it's different. Okay, you see from the other. This is the view from underneath. Yeah, let's keep that way. Yeah. So on the left side, do you see my mouse move? Does anyone see my mouse moving? Can I point?
I don't see it. Sorry.
Not yet. Okay. So on the left side where there is a gray box, that's the PSU. It's the power supply. And a power supply for let's say an NTX enclosure is not only providing power, but also ventilating the enclosure. It can ventilate the enclosure about 17 times per minute. So that was 40 CFM. So the idea is that on the left side, the air is blown out into the climate control device, then adjusted to the needs, and then blown in again. Oh, there's some hiccups on here. So blown into on the right side, there's a little tower with a yellow rim, and blown into back again. I have an echo here. Bojan, can you please mute, because I hear myself in an echo.
Well, I think it was from the stream. I don't hear it anymore.
Okay, got it.
Discord is not cooperating.
No, it is not. So I show you the climate control channel, where we also put some drawings so that you get an idea, if you did not follow up to yet. So we have a starting point, that one.
While you're doing that, I should probably point out that so the enclosure is done, the design for it's done, so there's going to be no modifying it whatsoever. So the climate control unit is basically going to be an add-on option to it. So we have to work within that constraint, whereas we have to make it work with this particular enclosure setup no matter what. So keep that in mind when you're thinking about it.
Yeah.
So, and we're also kind of trying to go for the most generic and available parts possible, because we've run into trouble with specialty parts just going out of production, and when that happens, we have to completely revise our design. So, like with the heat sinks, I mean, there's some crazy looking heat sinks out there for gaming and that kind of thing. We probably want to avoid that type of thing, just because those models come and go. It's the like generic type stuff like this that's been around forever and will continue to be around. That's kind of the direction we're going with some of this stuff. So just keep those points in mind.
Yeah, this is actually our core philosophy. We want to create hardware that can be purchased by anyone. So the parts of the hardware can be purchased from the shelf and can be assembled in an easy way. We only give design directions, and we produce parts that cannot be purchased, like an enclosure in that we cannot be purchased, or let's say the enclosure, the green stuff that you see now on the screen, can also not be purchased from the shelf. So we have to create this. In this case, what you're seeing here is just an idea for a prototype. So we are at the point where we about know what the solution will be, and therefore we are testing some devices and their interacting play. What I was doing in the last week was simulating airflow through a device like this, what you see, the green thing. You can imagine that when you put this underneath an enclosure and you have two openings on the very left side and on the very right side. So all the middle part where the fans are, where the peltiers are, this is covered by the floor itself, and only the left side, the opening on the left side and the opening on the very right side, this is then directly facing openings in the floor so that air can circle through. The thing is that what I want to discuss with you and Bojan and Brad especially is about the test environment, the test setup. You now bought some boxes that we can use as a let's say a test setup for the enclosure thing. And my idea is to cut holes underneath and to mount something like this green cover underneath and to, I don't know, glue it on or seal it on with silicone, something like that, for testing purposes. Would you think this is feasible?
Yeah, if the enclosures don't get here in a few weeks, it
Yeah,
sounds
and
like they won't. Then, yeah.
and actually, I don't want to cut on the enclosure. I want to cut in this mortar row for testing reasons. So
Oh, yeah, that's what I was meaning. The Home Depot box that me and Bojan both have.
yeah,
We could cut that all day. I don't want to cut the enclosure.
yeah. So this is 55 centimeters in length. I have to cut it in 3 parts so that it can be 3D printed. And yeah, after 3D printing, we have still to glue it together somehow to create this prototype. You think it's feasible?
But it is feasible. But before we get into that, we have to determine the final shape of it and how many peltiers, the size of the heat sinks. Those have to be standardized, and then later on we have to standardize airflow because we can't be comparing apples and oranges with airflow.
Yeah.
So I think the first step is to get the shape of the thing down, and I think the shape of the thing is going to depend on how those peltiers are mounted and how those heat sinks are sized and cooled and that kind of thing. So we're not quite done the shape yet. You got to figure that out.
Yeah, right. Thing is, I tried to simulate the airflow, and what I found out is that it's blowing to the fan, to the peltiers, is much better than sucking from the peltiers. Because on one hand, the fans wouldn't be a barrier, and on the other one, they wouldn't heat up. So to blow directly away from the heat sinks and the peltiers, I think is the best solution to go for.
So, quick question, Richard.
Yeah.
The top fan you have shown in the loop, is that representative of the excuse me, is that representative of the PSU fan?
Yeah, right. Exactly. Yeah.
Okay. The PSU fan going out of the output, that's what, 40 CFM?
Yeah. Plus
That's
a little
the
fan that
target.
sits on the nano, which is about 15 CFM. So if you just add them up, theoretically, then you come up to 55, and I've chosen 55 CFM for that rotor here.
But we're trying to maintain the loop at that CFM, just so everyone knows.
Yeah. That's the. I mean, if we talk about using PSU ATX PSUs, they all are around the 40 CFM. They have all the same size because of ATX design, and let's say with the 120 millimeters, you get 40 CFM rotors. So what I want to say is, it would not it would not change the setup, even if other people buy different PSUs. It would still be the same. And we will still have the same situation that the fan from the CPU of the board will blow into, so adding up the CFMs. So I think from the values, the simulation is correct. But yes, on Fusion I can only simulate heat, not cold. So I can only address airflow and optimize this. So one point, I mean, we have several points of discussion. So anytime, yeah, guys, back to, I'm not sharing screen anymore. Whenever you have a question or want to add something, please raise your hand and tell me, yeah? So one thing is also to have the possibility to get stuff out of the enclosure, to maintain the not the enclosure, the climate control device. So if something is getting caught inside, like let's say an insect by chance, and it should be easily removed. And my idea was that because on the intake there is a filter, so anything that goes through the closed loop will end up at the filter, and then by stopping at the filter, falling down. And I think there on the right side where we enter the intake, we can make a kind of an opening that can be once in a while, can be opened and to get the stuff out that collects itself. So it's kind of a self-cleaning function there by that. So the question is now, we are standing at the point where we can still discuss what parts we use, and Bojan already acquired the controller and some sensors. And the open question is how to set this up so that we can monitor from distance, right, Bojan? This was your question last time.
Can you say again?
Your question was your setup of the ESP and the sensors with
ESP32.
Yeah, with a stream, with a logging, so that we can access the data from outside.
So everybody can monitor what's going on.
Okay.
So yesterday, Christian gave me the site. So this is like a free software, so I can share data, graphs, stuff like that, you know. So probably tonight I will have setup, you know. So this is just a beginning, you know.
Okay.
ESP32 and DHT11 sensor.
Mm.
But we're gonna test different sensors. We'll see how it is going. You know.
So basically, we have to have at least 3 sensors. This is temperature, humidity, and airspeed, right?
Airflow.
Or air pressure. Yeah, you can use a pressure meter as well.
But also, what I find out, you see, this is, let me share screen.
Yeah.
Did you see, guys?
Yep.
Yes.
The bottom line is temperature.
Mm-hmm.
The top line is the humidity.
Mm-hmm.
So what's happened? The airflow can affect reading on a humidity sensor.
Mm-hmm. Is
So
this
when I put
is this
this on,
is this on your table only?
I'm sorry.
Your sensor, is the sensor openly lying on the table?
Yeah, now, yeah, but now I'm gonna put sensor in a box.
Yeah.
Without, disturbance from anything,
Yeah.
And then,
Mhm.
and I have much better stable humidity sensor reading. But this can take for a while. Hold on. Because I reading you see on the right side is coming, and after a while will be very stable. So reading like every 2 seconds.
2 seconds. Okay.
Yeah.
We
So
need.
this is my problem with this sensor, because you have, if you have put this sensor close to fan, or if you have airflow inside the box, this is gonna somehow hurt a reading. I don't know how a reading on a reading on the humidity sensor.
Mhm.
Mhm.
Now, this will be closed system, so we're gonna control peltier and fans by we have 2 variables. First one is temperature, second one is humidity sensor.
And third
So,
one is airspeed. We can control the fans as well.
Yeah, we can, we can.
Bojan, one
But
question. You're using an ESP. How many channels does the ESP have? How many sensors could you add to it?
Oh, this is I2C. I2C interface. So I can have, because I2C, you can put, this is only one line, so the data line. So so when you're dealing with I2C or SPI, you can put many devices you want, as long each device need to have own ID.
Yeah.
It's some kind of daisy chain, not as SPI, but
like
you
a
have
CAN bus.
you have a server and you have a client, and each sensor is connected directly and addressed directly.
Yeah, this is I mean, standard now. This is easy. And then now we're gonna use data. You see now, you see my screen inside the box with no airflow. You on the right side, you see how stable is stop reading. The
Yeah, of course.
Yeah.
So we need to figure out. I don't know. So I need to turn the fan somehow to see what's going on. Maybe in a room I have fake reading, but maybe even if with airflow inside the box, I will have stable stable reading on a humidity sensor. So this is question for probably the Christian will help me on a software side. How can we make a control loop, controlling the temperature, humidity, So yeah, this is what's going on.
My question about the multiple sensors is, I'd like to see a sensor before entering and after entering the climate control
Okay,
device.
I will order today. I will order today this Adapruit, the sensor. Also, I will order 2-3 more of those DHT22, so I can playing around different place.
Yeah.
So this is
Christian, what is the Adapruit costing? Any idea?
How much?
Go ahead, Bojan.
I don't know how much you guys. Just a second.
Because we need for a testing setup, we need sensors at the entry and at the exit. So if you go for an Adafruit weather station device, we actually need two.
Well, my question is, okay, input is like a outside condition, right? You're talking about that.
No, input
Wait,
into
no.
input into the climate control device as is, which is the output of the enclosure. It's a closed loop. So
Okay, no problem. You can put many sensors you want. You know, so
yeah, the question is this Adafruit device, first of all, is it the I2C device? And if not,
yeah, I think so. On SPI. I mean, doesn't matter. Doesn't really matter. You know what kind of interface. I mean, this is
yeah, okay. But I just
my
want to.
priority is good sensor. You know.
Yes, of course. And not only the good sensor, but I want to stress the point that we need the sensor on the entry and on the exit of the device.
Yeah, at a minimum, you need two sensors.
Yeah.
Tomorrow I will receive another DHT, so I can put outside, inside, whatever. You know, 2-3 sensors and see how this works. You know.
Yeah. Okay. Okay. Thank you.
And also another. Okay.
No, go ahead. Go ahead, Bojan. Tell us.
Yeah. Also, oh, I forgot now. Whatever. Will come back to me.
Yeah. Okay. No
Go
problem.
ahead.
Brett?
I just saw that they do not produce the Ardu Weather breakout board anymore. We have to look for something else, but they provide weather detection sensors like combined humidity and temperature and pressure sensors. So we can go for that. They lay around between 6 and 10 euros.
Ah, okay. Okay. I thought it is a bigger device. Okay.
No.
This is just a small board.
Okay. Good stuff. Brad, you mentioned an issue this week about mounting the peltiers in the ABS wall.
Yeah, and Bojan, would you mind stopping your stream?
Oh, yeah, I'm sorry. Yeah. Stop sharing. Where? So, stop. Yeah,
Yep.
stop sharing.
Stopped.
Okay.
Yep.
Okay, so try to share mine. Okay, do you see that?
Yep. Coming in.
Yep.
I don't know what's wrong with my Discord today.
It is shared. You can go ahead.
Okay, it's not showing up on mine. All right, so for the duct, the main body of the climate control unit, we're looking at it's 5mm ABS, so it's pretty thick. The nominal thickness of a peltier module is about 3.75 millimeters, so there's a bit of a gap there that we got to close. Also, the way, I mean, we're setting this up as like a forced convection heat exchanger, right? Pretty simple.
Yeah.
You've seen these in commercial buildings. You know, you look at the heat exchanger in a duct. It's basically filling out the whole duct, so you have that maximum amount of surface area to do heat exchange across. That becomes problematic with peltiers. I think the way Richard has it shown now is that we have very large heat sinks on the interior, and then we have almost equally sized heat sinks on the exterior. That's kind of what I have shown here. I just threw this together like at 6 this morning, so it's a bit rough. So the reason you don't typically see equally sized heat sinks in a Peltier cooler type setup is you have the problem of contamination of heat across your barrier layer. So, I mean, if we have on the outside, we're running it in cooling mode, so it's hot outside, cold inside. You got your hot heat sink here, your cold heat sink here. Peltier in the middle, there is this custom standoff piece of copper that we would have to source to clear this gap if we mounted it directly to the 5mm ABS. But you can see the problem with a large cold side heat sink is it can easily get contaminated from heat just conducting through the ABS material. This heat sink is going to get very hot. So if those peltiers, those heat sinks are touching ABS, there's going to be a lot of heat transfer between those two, and it's going to cut down the efficiency of the system. So if you were to go to a smaller heat sink and seal it off and try and limit conduction as much as possible, you can get a little bit better efficiency. But you can see the problem here is the footprint of this is only about 40 by 40 millimeters, and they tend to run 40 by 40 square, and maybe you can get them 30 millimeters high. What's the cross-section area of our duct, Richard?
8,000 square millimeters. But
so we wouldn't be covering the entire interior of the duct.
Yeah, I got it. I get the point. What I did in my design is I used your copper standoffs, the 1mm on both sides of the peltier. So that would increase the thickness of the peltier to 5.75 millimeters. So it is.
But it would be better if we could get the hot side completely off of the structure of the duct.
Yeah, but we don't have only one hot side. It is a dual mode device. We're switching hot and cold.
Yes, so I'm exterior versus interior. The interior side need to be smaller. So I'm just trying to think of this only in terms of cooling mode because it's easy to make heat. The difficulty is going to be making cold.
Yeah.
So I'm only going to be thinking about things in cooling mode in my mind when I'm talking now.
What about designing a frame, a tiny little frame that's just a little bit bigger than the peltiers themselves, to set the peltiers inside this frame, printed from plastic, and providing a kind of a standoff so that the heat sinks are separated from the peltier with this copper plates.
So one of the problems with the copper plates, it'd be great if we can get them within 1mm because they do more in terms of spacing. Yep. But every time you add an additional layer, so you're adding this gets to the issue of do we use thermal grease or use thermal glue? Yep. I can tell you thermal glue is kind of a pain in the ass. It doesn't spread easily, and if you get it too thick, you're going to limit your heat conduction.
Yep.
So every layer you're adding on top of that peltier plate, either the hot side or the cold side for spacing, you're going to lose in terms of efficiency. And remember, we've got someone who's going to be like me and makes a mess of thermal paste and glue, screwing this up completely because our users are going to have to build this on their own. So every layer we add to that adds the likelihood that it's going to get screwed up and perform suboptimally. So I would, if we could avoid using spacers in the design, that would be fantastic. I don't know that we're going to be able to, though.
I get your point. But this
implies if we can find a way of doing it, it's worthwhile.
Yeah, I get your point. But in this case, it would reduce the interior heat sinks down to the size of the peltiers. Which is not so good.
Which is not so good. If the thermal exchange is a function of the difference in temperature and area, and we're kind of limited on area, we have to get the small heat sink very, very cold.
Typically, when I've seen these configurations, there's a fan mounted directly on the cold side, pushing air through it. On the hot side, usually no fan. I'm speaking very generally, but and then when the unit reverses and operates in heating mode, the cooling fan can turn off because the system's able to, it's pulling heat from the outside. So I would think you'd need to have a fan directly on that cold side. I think in the configuration that was shown, the fan was somewhere else in the enclosure. I really think that's going to have to be right on the cold side of the heat sink in order to get that ideal delta T.
Yeah, actually, the idea is
may
to
I
have.
say something?
Hold on, Bojan. One second. The idea is basically to have a cooling, a climate control device that has fans and peltiers and heat sinks. So in order to control the fans and their air pressure and controlling the heat on the peltiers and switching the sides of the peltiers gives us the possibility to apply for any weather situation or any climate inside the enclosure climate situation. But yes, we have to blow anytime, no matter whether it's heating on the heat side is inside or the cold side is inside. We have to blow the air to get the air into the enclosure, because this device is on the exterior of the enclosure. It's like a piping underneath the enclosure. It's not part of the enclosure. And that's why by these two openings on both ends, we create a closed loop, which exchanges the air from inside of the enclosure into the device, the climate control device. There it be conditioned and blown back into the enclosure. But it's a cycle. It should always cycle.
And we'll never turn off the air completely in the loop. So the PSU fan is running always, no matter what. If the system has power, it's pushing some air through that loop. So there's always going to be some amount of air that's going through these heat exchangers. And say we are in heating mode. So the cold side is on the outside, the hot side is on the inside. Say it reaches its optimal temperature and shuts off. Well, if we have equal size heat sinks on both sides of our thermal barrier, the wall of the duct, well, that just became a refrigerator. So it's another ding against using large heat sinks on the inside and outside, because it's just going to be a conduit to cool it off. When you're in heating mode, and it's just going to lose all of its heat to the outside through this heat exchanger.
Are you sure?
Not a very efficient system.
I mean, in a closed loop, it should balance it out by itself, because we say, okay, it's not 100% hermetically closed, but there's really few air exchange from outside and humidity coming in. So I'd say when you start this, you should, within some minutes, come to a very stable temperature and working process, wouldn't it?
So if it's minus 10 on this side, and it's we've got it heated up to whatever you had it at in your simulation, like 20.
Yeah.
It's not so much that will it find a balance. It will. It's just how fast that happens, I think, is kind of the point that I'm trying to make here. Is
and where it finds the balance out.
Yeah, and you're going to be moving air through it all the time. So as soon as you get that balance, it's basically a refrigerator. It's losing heat to the outside environment.
Yeah.
Minimizing the size of the heat sink doesn't solve that, but it helps that. And I think our focus needs to be on, like George said, I mean, trying to maximize delta T for cooling applications.
Yeah.
So whatever tricks we have to do that, I think that we got to focus on that.
Yeah. True.
And that's kind of why I brought up having a fan directly on the heatsink inside of the closed loop portion, in order to extract as much thermal energy out. That would maximize the amount that you're able to take out of the system, having a fan directly on that heatsink. inside of the
Yeah,
um,
absolutely.
cooling enclosure.
And we actually have 4 peltiers inside. I mean, the prototype will start with 4 peltiers. Maybe we end up with 2
Okay.
peltiers. And the thing is that from my analysis of the airflow, it makes sense that the peltiers that are in serial, so after each other, are a little bit, how you say this, set apart, so that the air is not going through both of the heat sinks, but the second heat sink is, let's say, 2 millimeters off of the axis, so that air is very turbulent when touching the heat sinks and not laminarly flowing through. Okay. Yeah, we have to test this anyway to find out.
Which would be great if we could find a CFD simulator that would help us out with this, as opposed to what I'm doing now.
Yeah, my
Or we could actually
simulation
simulate.
would calculate 600 hours. I stopped it.
Yeah, I know.
Bojan, you wanted to say something. Sorry. Bojan. Bojan, you there?
Yeah, just I'm thinking. Yeah, are you hear me?
Yes, of course. Go ahead.
Yep.
Instead, heatsink. We need to. I think in many applications I was reading and online and white papers and whatever. The many people using plate on a cold side instead heatsink with ribs or whatever.
What application
Maybe.
were the plates used in? Was it like they were component cooling?
No, like the different kind of application, but most people using plate instead on a cold side. Plate. So you have mass on a, I don't know why. And not blowing air through the cold side. Just let natural.
But we're not trying to cool a solid object. We're trying to cool a fluid medium. So in my mind, you would need as much surface area
Yeah.
in contact with that medium as possible
Absolutely.
to accomplish
As
heating.
much mass flow through it as you can.
So I will go this week. I will set up the peltier, but I will instead I will have plate on a cold side and see how this works.
I don't think you gain anything. You can use it for a wine
Like
cooler, maybe.
solid aluminum plate, which is I have on my gym. So I will use like a CPU heatsink on a hot side, and then a plate on a cold side. So you see how this works.
Yeah, but guys.
Also, I reading.
Okay.
Sorry.
What I want to stress
Also, I
is,
was reading.
Bojan, sorry, may I interrupt you here? I have to stress the situation. We do not have a cooling situation. We have both. It has to cool and heat. Okay, so we switch the modes depending on what the circumstances are. So
Yeah.
it doesn't make sense to say we use a plate for the cooling situation, and what then when we have a heating situation? Bojan, you there?
But put it this way.
Yeah.
You know, freezer.
Yeah.
Regular kitchen freezer or whatever. They don't have a fan, right?
Yeah, they do. It's a compression system.
I'd
so
say
the
it's
fans,
compressed air and it's blown in.
Yeah, it's the fans on the backside. It's pushing air through a heat exchanger. All the heat sucked out of the system is pushed out the back or the bottom of the fridge.
Yes, yes. You blowing out the heat, but not inside. I'm talking inside the freezer. You know what I'm saying?
Yeah, okay. There's no fan inside the freezer for circulating the cold air.
No.
Okay, then this
No.
then the freezer is only has walls and the walls are cooled. right? Because a freezer is completely hermetic.
So as if I may, analogous systems go, we're not making a freezer, we're making an air conditioner.
Yeah, right.
So it has to have fans. We can't just rely on. It's forced convection. That's basically what it is. It's got to be forced convection.
Yeah, okay.
Right.
And as far as analogous to, this has a much worse thermal efficiency than just about any kind of heat pump.
Yeah, it's terrible.
So it's quite a task. My one big question was the estimate on the total thermal energy, like worst case, that we would need to dissipate. I think I'd read in the chat it was like 250 watts, something like that.
Yeah, that's what I put through a calculator. That's 3 sides in full sun, and that's with I found some insulation that we could use, and I adjusted for the thermal conductivity of that, and I put that on every wall, and then I put 100 watts of power inside it. Did not factor in the power needed to run the peltiers, which is another thing that's for a different day. But yeah, I would. That's how I got that estimate.
Yeah, but that is on the outside, hopefully.
And that is also calling for a 15-degree difference. Like it's 35 C on the outside. It was like 20 degrees C on the inside. That might be a bit of a reach for us to achieve that kind of separation. So that is an absolute worst case scenario.
Lionel, you wanted to say something?
Yeah, thank you. What's the component that needs climate control? Is it just the Jetson or also the camera?
Christian can answer this.
Good question.
Okay.
Can you
Both.
repeat? I didn't hear right.
Both.
I was asking what component needed the climate control. Is it just the CPU or also the camera or everything?
The
Just
answer is
just a microcontroller.
no, not really. No, the optics needs it because we do not want to have dew on it. The camera needs it because it needs a stable condition. It must be dry because if the temperature falls below 0, then humidity will fall down and freeze, and this is bad for the chip. Because normally in astronomy cameras do have a glass plate on it with a heater, so they do not so humidity can't freeze on the glass cover of the chip. And you need it for the electronics as well. So having stable conditions grants us the possibility that no dew is on the cover, no dew is inside, and everything can work under controlled conditions.
Yep.
Thanks.
Yep. So thanks, guys. I'd like to round this up for today for the climate control discussion. I mean, we are certainly going on discussing this in the respective channels here on Discord, but I think it's good that we have in some intervals some chats about it, going more deeply maybe into the future. So I want to stop this now for the climate control and head over to the machine learning and let's say the all-SkyCam part. And first of all, hello, Paul. Paul is there. Hi, Paul. Yes. Can you say something that we hear you?
Yes, can you hear me?
Yeah, now we can hear you. Okay.
Great.
One question, Paul. Would
Hi.
you please turn on your video? Otherwise, I cannot see when you want to say something.
I got background noise and family, so I'd rather not, if that's okay. I'll just raise my hand or something.
There's no raise handing feature here in Discord. Okay. You have to scream in, otherwise I can't help.
Yeah.
Okay?
Yeah, okay.
Okay. So, hold on. It's getting hot here. Now my heating works. So then the next hour we will focus on the stuff that Mike and Paul are working on. That's the machine learning, and Christian, that's the machine learning and identification stuff. I want to say two things at the very beginning. We have some topics we want to meet today. One is how we can proceed with the machine learning per se, and going about a training material, using that training material we have, or creating a new material that has to be discussed. Another thing is the experiences that Christian and Mike had with using the Nano and existing OpenCV library, for example, and running into performance issues. That shall be addressed today. And yeah, whatever else you guys come up with. So to start it off, I wanted to first ask Mike and Christian, because you two had experiences or worked with the Nano and camera and video material that did not satisfy from the performance side. Can you, just for the audience that are sitting here, just summarize what the issue is? Christian, maybe you start.
Okay. I was working on the All-Sky camera system, where we chose to have this, this nice fisheye lens from Pergear. I produced a 3D printed adapter to put it together, and I was working. This adapter has a 1.25 inch hole in it, because that fits the astronomical cameras we have on hand here, and that will fit the IMX whatever cameras too, because it's kind of standard, and we can have some basic way of focusing it, so it's made up for all kinds of cameras we will use in the future. Then I hooked everything up to the Jetson Nano. Every camera we had on hand, there were 4 of them. Both I showed here, and from the imaging source we had an IMX 335 and an IMX 226. Let me go from top down. The RZ1600 Pro is a 16 megapixel camera, and the buffer of the Nano is too small to fit a video in. It said, okay, no, it won't do anything. The RZ120 Mini has got 2 megapixels. It's full HD. This is working fine with about 30 frames per second. The IMX 335 is a camera that is hooked up with a deserializer to the Jetson Nano, and I couldn't get anything out of it. It was on, but I couldn't recognize anything. The software stuff, TIS cams are provided with a disk image for the Nano. I couldn't get anything to run on that part, so I skipped it. And the last camera was the IMX 226 with 5 megapixels, no, 12 megapixels, and the frame rate was down to 1 frame per second. So the only camera that worked fine was the RZ120 Mini with a decent frame rate, but with a pair gear lenses that requires an APS-C sensor, we just have about 90 degrees of field of view. So if we don't find any suitable camera that goes with an, let's say, 1-inch chip, we have to look for other suppliers. And so Richard and I agreed on skipping that part of the fisheye view. We're using the fisheye optics, but we're to develop the streaming part, because this is important now. We will take just the cameras we have and get them running. And this is the main road we're going now. So the Jetson Nano might be too small for that.
Mm-hmm.
This is where we stand now.
And you say the buffer of the Nano is too small, no matter
Yes.
what library you're using, or
Yes.
it only is capable of 2 megapixel video streams.
With a frame rate of 30 frames per second. It can use a 12 megapixel camera like the IMX226, but then the frame rate is down to 1 frame per second.
Okay. So performance-wise, we have to say that when we design our all-sky cam, the camera itself, the fisheye, we have to at least go to 12 megapixels. Otherwise, there's a mismatch between the optical resolution of the fisheye lens itself and a resolution of a sensor.
Yeah.
It has to match.
Due to the Nyquist-Chen criteria, it tells us what resolution of the combination between camera and optics we have to choose to get at least our benchmark ISS recorded on 1 pixel.
All right. Okay, so that means
and on the
that.
processing side,
Pardon.
sorry, go ahead, Richard.
No. Go ahead, Brett.
On the processing side, do we kind of have an idea for the minimum FPS that we want to achieve? Like, 1 is obviously not enough. What's the upper bound?
We should lay around 25 to 30 frames per second, because we have to calculate some kind of vector to pass it to the PTZ. So if the timing resolution is too low, we can't calculate the vector.
Mm-hmm.
Thank you.
But would you say that a 15 FPS would be sufficient? Could be sufficient?
If we correct the vector by some assumptions, we might reach some kind of goal there. But we have to try that out.
Yeah. Lionel?
So when you say vector, do you mean that you convert the square image to one long vector?
No, this vector means that you calculate a movement path.
Okay. So the processing, that's why we're talking FPS, is that because the processing is done
on the
very
fly,
early.
yes.
So we're not talking about acquiring frame, we're already processing them as we stream them.
No, we can't use just 1 frame because just 1 frame is a position on the chip, but we have to use several frames, let's say 2 or 5, to get the first hint of a direction where the object is hitting. But that is not enough, because if we will catch a UFO, this can turn in any direction at any moment. So a 90 degrees turn could be possible. So if we catch some object that is performing such a movement, then we have a UFO, of course. But let's take the ISS. The ISS has, and this is because we can use it as a benchmark. It has a certain path over the sky, and it does that every 90 minutes. So we know exactly where the ISS should be. If we can record it, it shows that we did a good job.
Mm-hmm.
But let's take a plane that is about 50 kilometers away, let's say a 747, and that one is low above the horizon. Then we have a very, very bad situation, because the lower the height is above the horizon, we get much more air mass and therefore refraction problems, and we can't determine position and the movement path very accurately. So we have to keep that in mind too. And if the resolution is down and if our camera is too slow, we can't calculate the movement path at all. This is a very great problem, a very huge problem when you want to track the path of a meteor, because of the air mass you have to face, and the speed a meteor has is a second problem, that because you need a high frame rate and a very high resolution for the camera, so you can track it. Or you're doing it like amateur astronomers. You set up the camera in one direction and just use a very, very high exposure time. So you record the complete path. And we can't use that because we want to point the PTZ to the object as soon as possible to record it in detail. Because let's say the ISS is our benchmark, then we can record on the all-sky cam the ISS with 110 meters in diameter at a distance of 422 kilometers as just one pixel. And this pixel has to move to a second pixel so we can detect a movement. And we need at least 11 pixels to get a usable movement path and direction. And since this is all in a sphere, we can't use just an X and a Y position to determine where it's moving.
Anders here, I have a question. The Raspberry Pi HiQ camera, that's not usable here, or?
Not really, because the diameter of the optics has to have a certain size because of the resolution.
Okay.
And the covered chip area is way too small. It just has, I think, it's a 2 megapixel camera. And we need much more pixels, and they have to be very small for the resolution.
So all these combinations of several small webcams, like Wise cams, which was discussed some weeks ago, doesn't make sense, because if the resolution of the optic is too small, you just don't resolve this stuff there, no matter how much resolution your sensor has. Brad, you wanted to say something?
No.
No, okay, so misunderstood it. So okay, so this is one issue that we are going to solve by finding the right manufacturer for providing the right camera and so forth, and then to find or if we have to skip the nano and have to go for the NX, for example, then so be it.
I have a question.
Yeah.
I was wondering, the University of Würzburg in Germany, they seems to be working also in detecting UAPs. They set up systems on their roof, and I was wondering, I mean, do you have some collaboration with them on because what they have selected there?
Christian, Kaya.
Yes, we have.
Okay, fine.
In fact, I've got a friend there who was a student of Professor Kayal, but they didn't get back to me yet. I think tomorrow or on Tuesday they can get back to me. But it seems that they are using the old SkyHub setup for it.
Yep.
On their website, you can't find anything about the camera they are using, and I think it is because they do not want to. They do not want to say, okay, yeah, we're using the SkyHub systems, because then they would have to credit it because it's a university.
Right, but they have master thesis and bachelor thesis. They're listed there on the site. So I mailed Professor Kayal and see if I get a response from him on because this should be open material.
Okay, good.
Yes,
good
it
start.
should, but then they have to get credit to SkyHub, and SkyHub is not existing anymore, and
They don't
I
have to
don't
name
know
it.
how that will go. But yeah, I did it the way around the team members, and hopefully tomorrow or Tuesday they will get back to me too. So if you get an email round out and I get the information, it's good to compare it so we can verify that they didn't say something that we don't want to hear.
They should be interested in a collaborative effort here. I think they should be. I mean, that's my idea. But
we discussed that one too, but at the moment, Professor Kaya is member of some other groups with Avi Loeb and several other things. I don't think we will get him to a good collaboration soon. But
So
we have to evolve further so that we can do that.
I just posted a link on in our DMZ channel. I guess they updated their website. I don't know. They've got a cutaway of their setup on the roof there at the university, and it doesn't look like it's a Dahua. It looks like it's something else. So just FYI, I put that link in the DMZ channel. You can click on it.
Yeah, the problem is that they are cooking with water too, and since we are facing problems of getting the right camera, they will too. And they are not using some kind of PTZ as an external device to look into things further. Yeah. And as I know, they didn't really record the ISS. They recorded a 747 that just passed from Frankfurt Airport. And this is not very far away. So their resolution is very, very low, and they won't have the chance to detect the ISS with that equipment. Because of Rayleigh criteria and Nyquist-Shannon criteria. These define if you can record something and have the right resolution on the chip.
Lionel?
Yeah. I just want to show you something I worked on a previous project. Those were stereo webcams. So that's two webcams stuck together, and so it didn't do UAP detection. It was used to detect ranges in photo, to detect object and to say how far the object is. And so I tried with that setup, and we reached I think 60 FPS on a very low resolution, so 320 times something like 320. And the hardware we used was an Intel NUC with OpenCL, and so there was some processing done on the image at 60 FPS. Slower resolution, but it's something I was not the one coding it, but I seen the guy do it, and he reached that very high processing after a few months.
Yeah, but the resolution of the optics is very, very small. Did you try to use it on a 747 in, let's say, 200 kilometers away?
No, it would not work because those were the webcams from the PS3, and those were used for dancing in your living room.
Yeah.
So
it's the same.
That's the something else entirely. But
that's the same reason.
The one developer.
That's the same reason why people fail with their smartphones to capture UAPs. So it's always the question, why do we not capture UAPs when there are so many smartphone cameras outside? And the simple answer is, although the resolution of the cams is high, I mean, they go over 100 pixels today, the size of the optics is too small. That's the issue. So we have to use a bigger, let's say at least 30 millimeter diameter optic to be able to resolve the ISS at all. No matter what size the sensor is, the optics is crucial. And for knowing that the optics is crucial, Christian is smiling now, but that the optics is the most important part. It defines the size of the sensor. So we should not look at from upside down, but from top downwards to take the optic as the factor for resolving a UAP in a distance, and then finding the suitable sensor for it.
You can have a try. Go out with your smartphone and try to take a picture of Jupiter. Jupiter is above the horizon now, and it has 1.7 arc minutes in diameter. So if you can record it with your smartphone, then you have got no chance of recording the ISS, because the ISS is just half the size. And this can't be done with a smartphone, even if you put a magnifying glass on it. I tried that. It is impossible, because the diameter of the optics defines the resolution.
Yeah, it's the limiting
That's
factor.
why we are producing a 40-meter telescope. 40-meter telescope. And we do not have to do that if such a small camera or such a small optics of a smartphone could do the work.
Boyan has a question.
Yes.
Okay, I have a question for Christian. Okay, and for Richard too, because Sky 360 is we are try to recording the objects in an atmospheric, right?
And low Earth orbit.
So, yeah, but we have our reference is ISS.
Yes.
Why is that? Can we have lower reference?
If we can record the ISS, any object in that size, in that distance, can be recorded too.
Oh, okay.
So,
okay, just asking.
It's technically possible. The only thing is we have to find the right equipment. It is there, I know. We could get it, but it would still be too expensive. I mean, I could get what Christian would like to prefer is a 1,500 euro fisheye camera, which is not feasible for our community. So we are scouting for something on a board level that is, available. That's the most important thing, the availability. But George wanted to say something.
Okay.
My question was just the next step up from the Jetson Nano. Which Jetson is that? Which model? I think you had mentioned the Jetson X or NX.
NX.
Yeah, so NX is the X.
Go ahead, Paul.
Sorry, guys. NX is the next step up, and then AGX is the top line. But what's interesting is they're bringing out a new versions of all three of their hardware, which should be out Q1.
Really? Okay.
So hopefully they stay sort of similar cost to the three existing, but just increase the performance.
Is there a big price difference going up to that next Jetson module?
So going up to the existing NX, yes. I think it goes up from like $100 to sort of $500.
This is an NX, and I got it for like $400 tax and shipping this summer.
Mm-hmm.
It's now some stupid price because of the chip shortage. I'm hoping that goes down. But yeah,
I ordered one, but couldn't get it.
Yeah.
Okay.
Just a mention about chip shortage. This is the game.
Yeah.
Since I'm working with electronics, I mean, this is stupid. Somebody makes a lots of money making chip shortage.
Yeah,
This is not
that's an
true.
issue. Yeah,
You
you're
can,
right, Bojan,
for
but
example, just okay.
no,
I'm
Bojan,
gonna stop.
we do not have to
Just
talk politics. We don't have to talk politics here and world market politics. We know this is an issue. We just can't help it.
No. I'm not talking about. No. This is, no, I'm just saying. I'm just saying. Uh, chip shortage is not true. You can find another way. You can find anything you want. So this is. I'm not putting politics or stuff like that
Okay.
in this discussion. Just
Okay.
to say, because I'm hardware guy, I know exactly. Then we can find any chip anytime, no matter what they say. So I'm not putting politics. Sorry,
Okay.
this is misunderstanding.
Okay. So I have to talk with you the next days. You have to help me in procuring. All right. Okay.
And I request a public apology to me from you, Richard.
I
I'm
will. I
joking.
will
I'm
certainly.
joking.
So, okay.
I'm
Let's.
joking.
So let's jump over to the next
No.
bullet is the experience that Mike and Christian are having with the performance on the Nano brought up the idea of using other libraries like VPI. And that's one item. And the other one is how we shall proceed on with the machine learning part, where we, on the one side, have a training material, which is, by the way, already shipped to Mike. He is now in possession of the training material as well. And maybe, yeah. So my question to Mike is actually, shall we talk about the VPI idea? It was just ventilated last time. You still have to do experiments with it, right? Mike, are you there?
Yeah, yeah. So basically, yeah. Can you hear me?
Yes, of course.
Yeah.
Okay. Yeah. So the throughput I'm getting on the Nano currently is per second without tracking and about 1 frame a second tracking, and there are quite a number of YouTube videos whereby using the Nano you can get a much higher frame rate, and I think that's possibly using the VPI library. So the cool thing is that we've recently refactored the code quite a bit so that the frame processing, the mechanism to process a frame is it's quite easy to expand on that and produce another implementation. So currently I have a CPU implementation and then I have a GPU implementation. And I was going to experiment doing a VPI implementation of that frame processor, and see if I can see what sort of performance numbers I get out using that. The I received the training material, so I'm trying to get into a position where I can process that. I also just I was having issues with graphics cards. I need a graphics card in order to try and kind of experiment with the ML stuff, and I was trying to procure a graphics card over Christmas, which didn't go very well. But I managed to buy a second-hand laptop with a reasonable graphics card on it, and I'm just busy setting my environment up at the moment so that I can get into a position where I can process that material. I'm hoping to be able to start this coming week to process it and see I suppose my two updates really is one is the VPI frame processor is to try and go and implement that, and the second one is to process the training material or process the videos to try and get training material. The laptop I have now actually processes that much faster than my previous machine. So I can probably get in the vicinity of like 25 frames a second. So processing that, I don't know how long it's going to take to process that material, but I've split it out into one, and yeah, I'll just see how I get on. I think I've got it. So I've got directories with 3,000 files in them. So I'll process one directory and then just feed back to you as to how long it took to process. I'll let it run overnight or over a weekend or whatever, and see what sort of performance I can get.
All right.
Quick question, just to make sure we're on the same page. This processing you're doing, that's just to separate the valid motion from clouds, right?
Yeah. So it's essentially because I know you had concerns towards the end of last year with regards to training material, Brad. Just and really it's to, and I know Paul's view is that the videos might not actually contain much valid objects to use as training material, but it was just I was just going to try and process it to see what comes from it, really.
Okay, just curious. Thank you.
Yeah,
George?
so that's pretty much it.
George?
In terms of the GPU performance, I've done some machine learning, and it was totally impossible on the graphics card I have. I ended up using a Google virtual machine, and was able to go from, it would take maybe 3-4 hours to generate 60 seconds of video to about 3 minutes to generate 60 seconds of video. So that's certainly an option if you're training and it becomes like, extremely long to train this data. It could be done on Google Cloud. I have an account on there. You also, I think, can set up an account. You get like 300 free compute tokens or something like that.
Yeah, no, cheers for that. I think I mean Paul's been more busy with their machine learning, so I'll probably ask if he wants to jump in there. He's probably a better one to kind of go through that. My focus has mainly been on kind of just the simple tracker and OpenCV and those sorts of things. I haven't quite got to the machine learning part yet. It's on my list, but I just wanted to get into a position where I could potentially run it locally by having a graphics card, but that's proved a bit of a challenge. Yeah.
But you, Paul, you're running it locally, right?
Hey guys, yeah. So I'm running it locally fine, but I've got a games machine, so it runs it pretty well. The problem for me has been more about now trying to find the right algorithm, the right ML algorithm to do this problem, than either getting training data or processing training data. My problem with the other training data was it was just taking me too long to find interesting stuff, whereas I've got an all-sky cam on my roof and I live next to an airport, so it's pretty easy for me to get interesting data. But now I've got that data, I've got a whole bunch of scenarios where that are too difficult for the current algorithm I'm using to give decent accuracy rates. So my plan, and I'm a bit delayed by sort of other life events at the moment, is instead of using the CNN algorithm, to use a temporal-based algorithm, so some RNN or LSTM, which will take into account the fact that these are videos essentially and use the temporal aspect. So at the moment, I'm getting the temporal aspect from the optical flow, but that's an additional calculation step that needs to be run on the hardware. Mm-hmm. So at the moment, we take two images, calculate the optical flow, feed that into the ML, and then the ML takes the optical flow and the current image and says, okay, using those two images, what's the interesting thing? So that's how I'm kind of fudging the temporal aspect of it at the moment. Mm-hmm. But there are algorithms that are more specifically designed for sequences of images, and they can take into account things that happened like numbers of frames ago as well, mm-hmm. as opposed to just the previous frame, which an optical flow image would show. Yeah. So they're more complicated, and I'm just getting my feet wet in the machine learning area. So I started with the RCNN and as a sort of starting point. But yeah, that's kind of where I am at the moment.
All right. Yeah, so that brings us to the point where we have a lot of open topics for the all-sky cam, and it will just take time to find the next solutions. Paul, you're working with your self-created material because of your fisheye cam on your roof, right?
Yeah, I've got the other material and I can process it, but it doesn't really give me anything.
Okay. Would it help you to have, let's say, a handful of videos that are interesting with real events, or did you already scout them out?
I've already got them.
You already got them.
We've put most of them in the repo. So there's a collection of 20 or so videos that are pretty interesting from a sort of, this is the problem that we're trying to solve. If we could do this, then I think we're in a good position. Okay. And I've got a few more on my local ones that I took recently. I haven't had a chance to upload, but okay, I actually think we've got most of the material that we need in order to move forward.
Okay, good stuff. Yeah.
So is that so are we saying we've got most of, so with the videos that we currently have, we should be able to produce enough learning material, but the problem currently is processing is the same, is just trying to process the videos to try and get a reasonable frame rate out of them. Is that
so?
Yeah.
I mean, ultimately, you need to be able to process these things at a fast enough frame rate to be able to do this sort of live. The RCNN is a large model, and there's no way that we'd be able to do anything like that. Even my high-end graphics desktop has challenges running that at high frame rates. So that's one of the problems. The other problem is trying to figure out which algorithm we should use and
okay.
Yeah, developing that.
Okay.
Really, the next.
Oh, sorry.
Go on.
I mean, I have a question for Christian. What is difference between night capture the image or day capture the image?
In the night, objects near the Earth only can be viewed or recorded when the sun illuminates them, or they have got some kind of illumination by themselves. In the night, if you take a look at, let's say, a comet or so, it is illuminated by the sun, but you need much longer exposure times, let's say up to 1 minute or so. And these objects are, because of the distance, moving very, very slowly. You can track the movement of a comet or a meteor, but it is slow compared with a plane. Let's say a 747 in the night sky has the same speed as in the day, but it has the beacon on and some lights. And so you can track it because it's illuminated too. But you need much more exposure time to record it. And we are talking here about seconds between 2 seconds and 10 seconds. And not in the night. At day, it's about, because of the illumination, it's about 1/250 milliseconds. This is quite short, but in the night, the exposure time increases very significantly.
So you're telling me of course you are astronomer, so the best way to observe the planets or stars is on a night, right?
Yes, because of the contrast.
Okay, thank you. This is all I need to know. Sorry, guys.
Oh, no, sorry. Okay, so we have two different levels of problems. We have the performance problem on the board to process the incoming streams, and then we have the issue of creating the right neural network that creates identifications on this existing material or on the feed that's coming in. We have to do this in parallel. We cannot wait for one for the other. So I think, Paul, you're totally, how you say, independent of whatever on the hardware side is developed. Mike, you're more or less in between. You are the in between guy.
Okay.
May I ask a question, Paul, first? What graphic card are you using?
3090.
3090, okay. Yeah, I'm using a 2080.
Okay. So
yeah, so I have to remortgage the house in order to buy a 3090 in the UK at the moment. That's the challenge we have.
you won't get it anyways, no matter what you pay for.
And this is why the cloud is so helpful, because you can use for some time a graphics card that you could never ever afford, like the NVIDIA Tesla P100 or whatever it is. That's just on an order of magnitude more computing power than even like a 3090. Maybe the 3090 is a little closer than what I'm using, which is a 970, which is ancient now.
One thing for Fusion 360 guys who using back on a May last year, I have problems, and then with my graphic cards, and I contacted the Autodesk support, and they told me, no, your graphic card is not issue because Fusion 360 need more processor power than graphic card power. I was stunned. I said, whoa, no. You need lots of processor power, but you need good graphic card for rendering. This is all. I mean, this is just information. You know, I get this information from Autodesk support. You know, so.
They are looking from a very different.
Wow, everything is frozen now. Can you hear me? Whoa. Oh, I'm. Oh dear. I have to reconnect. Wow. My whole setup is broken now. Oh dear. Hello, everyone there? Okay, I have to stop the recording now.
To run it before that we can record an event. So these algorithms have to run live on a hardware. And yes, afterwards, the archived material can be run on some kind of cloud service, of course. But since we have to use it in the field, we do not have that cloud service, and it won't run in real time.
I think that we're talking about two different things. I think one part of it is the training of the algorithm itself, which is typically done in the cloud, and the other part is the inference runtime, which we do need to do on the edge.
Question for Christian. If we filmed everything in infrared and convert it to black and white, would we have the same image day and night?
No.
No?
Because infrared means that you go by a wavelength between 690 nanometers to 1500 nanometers, and then comes the middle range infrared part, and that is going up to the far infrared part, and then we reach the radio frequencies. So where do you want to start? And this is infrared, and we try to focus on the visual part of the electromagnetic frequency. So yes, we can record some information because the cameras are sensitive to infrared up to 1200 nanometers. But as it is for the optical part, the infrared needs more exposure time in the dark than it needs at day because of the reflection of the infrared frequencies. So there, the things are similar to the optical frequencies.
Christian, I have a question. What is the best way to record or capture the event, whatever it is? Infrared, what is the best way to capture the unusual event?
It depends on what wavelength an object emits something. If you have got an object that is illuminated by the sun, then optical wavelength from, let's say, far ultraviolet to near infrared is suitable. This is where our cameras operate in. If you have an object that does not reflect any kind of visual wavelength, then you go by radio frequencies. And if you've got something that has very, very high energy output, then maybe X-ray or let's say gamma bursts are suitable. So it depends on what the object of interest is emitting. And since we try to go with optical cameras, for us, the optical part should be suitable.
And
Because
even if an object is only radio emitting or flying in its warp bubble, whatever that is, it is reacting within our atmosphere with the atmosphere, and therefore creating infrared radiation, which is then be able to be captured. So the effect, can be captured.
Don't mistake infrared as some kind of heating signature, because infrared covers a very, very large range of the electromagnetic spectrum. It goes from radio frequencies to optical, and the near infrared is optical ones. And the middle range is where all the FLIR cameras take place. So this is some kind of reflected warmth.
Yeah.
So
but it's not optical.
The bottom line, what is the best way? Okay, if we capture the UAP or UFO or unusual object, whatever. What is the best way to capture the object? Infrared?
It depends what it is emitting, what kind of radiation you've got. It can be if it is illuminated by the sun or something that emits light, let's say green light, then a detector within the green light spectrum is the best way of detecting it. If it just only emits heat, then a FLIR cam is the best way to do that.
So you're telling me AI, artificial intelligence, inside the jet zone, whatever, need to figure out what's going on.
It depends on the detectors you've attached to it. First thing is the detector. If you can't record an event, any object, then the ML part is useless because there is no information, there's no data that the ML part can work, can do its magic on. So you first need some kind of recording, and therefore the detector must be in the right range.
Yep.
So you need to artificial AI need to figure out what kind of object.
Yes.
I
Yes,
can
it
find
has to do pattern recognition, of course. Yes.
Yes. This is the. Oh my God.
I think Bojan is running in a direction where you don't find an end, because the AI does only work on the material that's already captured. So it depends on the sensor what material that will be. But the AI cannot decipher whether this is from infrared and this is from ultraviolet or something like this.
Yeah.
It's a material. Paul, you wanted to say something?
Hey guys, sorry, I got to jump. Now, I'm not going to have much time to work on this, but I don't want to block other people. So if there's anything you need from me, now I can stay for a couple of minutes, or I'll be available to unblock things as we go along. But I'm probably not going to be doing primary development on the new algorithm in the next couple of weeks.
All right.
The videos that you mentioned there in the GitHub repo.
That's right.
So
there's a vids directory.
There's a vids directory.
I
RCNN, Sky 360, RCNN.
No, Sky 360. Sorry, Simple Tracker vids.
Simple Tracker. Okay.
Anders here, I'd just like to add that also it depends on this UFO. If they're using cloaking material on the UFO, it means that also that the radar doesn't work. If the radar frequencies is going to be optical, depending on thickness of the cloaking material. So it's lots of variation. We don't know really what to expect and what to see. I mean, that's smart enough. They're using cloaking material which is quite broad banded, which means that the signal will more or less pass around the object. So
exactly. That's why we try to get every sensor involved that we can get our hands on, but it has to be step by step. We can't do it all at the same time. And that's why we welcome every developer that has an idea and is willing to do any kind of contribution to that. So yes, we plan on getting every detector that can do some remote sensing in place and use it.
How about magnetic sensors? The problem with magnetic sensors is that the object has to be very close in order to detect it. So I assume it's
that's the issue, right? Yeah.
So if it is in a range of, let's say, 2 or 8 meters, then we can detect it right now because our magnetic field sensors have a range up to 10 to 12 meters, and then they are not very, very accurate.
Also, a radio frequency sensor using an SDR
is planned.
Yes,
it is planned to use a passive radar system.
Richard, show the diagram of the concept.
Okay. Okay, hold on.
guys, I'm gonna have to bail as well. Okay.
Yeah, okay,
Is that okay? Do
absolutely.
you guys have
First
any
of all, I want to
questions
say,
for me directly or?
hold on, I want to thank you all for participating today. I'm going to shut down the recording now.